Hi, my name is John Rizzo. I'm a senior in the physics department. I did my research on detecting exoplanets in stellar clusters. My research advisor is Dr. Palen. This project is very much ongoing. We still have a lot of work to do, but we have some exciting preliminary results to share today. The inspiration for this project came while I was at my house watching YouTube videos, and they mentioned off the cuff in their video that very few exoplanets, that is, planets around other stars, stars other than the sun, had been detected in stellar clusters, and that struck me as a little odd. Um, Stellar clusters, in my opinion, would make an obvious choice for observing in order to detect exoplanets. And so I decided to do a little bit of digging, and sure enough, only a handful of planets had been found in stellar clusters. And I thought, well, that's a little odd because in stellar clusters, you have so many targets all bunched up. In one image of a stellar cluster, you may have 100 to 200 possible targets to look at, 100, 200 stars, each of which has a potential planet around it to observe. And so each frame has so much potential to find these stars. It also provides an interesting opportunity in another sense, because all stars start their life in open clusters, or at least the majority of them do. And these clusters disperse over a fairly short period of time, a few tens of millions of years. So it's a very good chance to explore young stellar systems, look at young planets, and get a better idea how they evolve over time. And I say look at very loosely here for a few reasons, because we can't really directly look at exoplanets. Um, Only the most powerful telescopes in the world have that capability. The Keck telescope in Hawaii, for instance, is 10 meters across, and it can barely make out planets around other stars by directly imaging them. So the rest of us have to rely on indirect methods of finding these planets. The method I chose to use, that I consider the easiest, and I say that with some serious air quotes because this is by no means easy to do, is called the transit method. And the transit method relies on the geometry of the star system. It has to be nearly edge on from our perspective to us. And so we wait for a planet that's orbiting a star to pass between its host star and us. And when it does that, the star's brightness will dip ever so slightly. Um, this is an example of a transit that we see here. This is a transit of WASP 33b. And this is about as good as it gets as far as transits are concerned. They all have this characteristic bowl shape here with that sharp dip followed by a flat bottom followed by a sharp rise back up. And that's important because a lot of stars are what are called variable stars. They change in brightness on their own, but none of them do so with this characteristic kind of cup shape. And a few more things to keep in mind is that these are short events. They last between 1 and 4 hours, and then they're gone for another 2 days, 3 days. And so you really got to get lucky with the timing of this whole thing. And they're not exactly large dips in brightness either. We're talking at the most 2%. WASP 33b here is a particularly large dip. It's a very large planet going around a very small star as it happens. But we can tell a lot of stuff about the planet and and its orbital characteristics from these dips. We can tell how far it is from the sun, how long its year is. We can tell how big it is based on the size of this dip. We can tell a lot about it. And so this is the shape that I'm looking for in the data. We want to see this characteristic dip shape. As I mentioned, it's a very small change, so we need really good equipment. We do have an excellent telescope here on campus, but unfortunately, it is not good enough for our needs. Mostly due to the atmosphere here in Ogden. The atmosphere is just too light polluted and too turbulent and too much smog in it to really work for us. So we used our OUR grant to buy some time on a telescope in Australia. And there we go, if the slides will go. This is the telescope we used. It is a 1/2 meter diameter telescope. It is situated at probably the best location it could have possibly been situated. It's at a professional observatory in Australia at Siding Spring Observatory. And so this is the telescope we used. We bought time on it. They only allowed us 4 hours a night of imaging time. And so, we'll take what we can get. And so we ended up imaging the stellar cluster Messier 41, or M41 for short, for 4 hours a night for a week. Unfortunately, we only got 4 hours a night. We would have liked much more because some transits last up to 4 hours. But we took what we could get. We took the data. The data is really clean, very good data. And we then took the data. We did some corrections to it to account for different thicknesses of atmosphere that we were looking through, differences in what's called atmospheric seeing and transparency. We did some corrections for that. And then we used a program called MaximDL at first. Now, MaximDL is a great program. It does have some drawbacks. The primary of which is that we have to click on every single star that we want to investigate. And that doesn't sound like a huge deal, but when you're looking for the smallest variations, you want to make sure you're clicking on the precise center of each star. And big, meaty human hands aren't very good at doing that. So MaximDL, unfortunately, isn't the best in that regard, but it is a very handy and powerful tool to use for this analysis. And so we ran our data through MaximDL, and I'm going to show you a couple of graphs here on the next slide of what that data looked like. All right, so here we've got a couple of stars. Let's ignore the bottom one for now. We'll look at this top one for now. This is what we would expect your average star to look like. It's a fairly flat curve. You can see no real variations in it. This is over the 4-hour period for one night. That dashed line in there is just a boxcar fit, so it's a way to kind of smooth out the data and see if there are actual variations in there, and we see practically none. That's what a typical star looks like. If we look at this bottom chart now, we can see there is a clear dip in it. It's a small dip, which is good. We're looking for small dips. But unfortunately, it doesn't have the right shape for it. If you remember, the transit of WASP 33b that we saw a few slides back looked more like this. Unfortunately, that's not the shape we see here. So we didn't detect a transit in this particular case. And so far, we have yet to detect any transits, unfortunately. But we haven't given up, and we have some ideas of how we can tease more information out of the data that we do have. What we're doing right now, as this is our next step, to try to go from 0 transits to maybe 1 or 2, is we're leaving MaximDL behind. We're writing some code in Python, specifically using a package called AstroPy. AstroPy is what professional astronomers use to analyze their data. So it's as good as you can get as far as data analysis is concerned. And we're writing this program in hopes that it will not only make our lives easier, but that it will produce cleaner data for us. And so this program will automatically detect stars in the image, will automatically do these atmospheric corrections, or what we call air mass corrections, to the data. It will automatically produce those brightness versus time graphs that we saw earlier. And then it'll hand us on a silver platter the most interesting of those graphs, and it will kind of ignore the flat ones. We're partway through writing this program right now. We can get it to automatically detect stars so far. So we've got the first bullet point checked off, and we're working on the rest right now. And then once we've got the program all polished up, we'd love to do another data run to look for planets in M41 and potentially another cluster now that M41 is no longer up. But it's exciting, and we're excited to hopefully next year present a transit. Hopefully. We'll see. Thank you.